Let's start. So today is going to be the first panel discussion of this last week of the Nordita scientific program on quantum gravity from gravitational spectral field theories to ultraviolet complete approaches. This last week is on quantum gravity phenomenology, and today in particular we're going to be thinking more in the context of cosmology, broadly defined. The panel is called Quantum Cosmology, and we have 5 different panelists with us today. We have Alberto and Salvio, who gave a talk this morning. We have Anne-Christine Davis, we have Kellogg Stelle, Robert Brandenberger, and Paulo Vargas Moniz. You see that the names are in alphabetical order by first name, and this is the order we're going to follow towards the end of my introductory talk for the people who, or for the speakers, for the panelists to give their introductory remarks. Just to be clear, so each panelist has up to 10 minutes, and please keep it to that because we want to have more time for discussion as opposed than just having a lot of introductory remarks. The panel is about 2 hours long. We're going to try to see and follow more or less the structure of, if you have a finger, you can actually make a quick comment or clarificatory question. If you have a hand, we can change the topic. So this is the guidelines for the discussion after everyone has given their initial remarks. I was kindly asked to chair the panel last week, and since the panel discussion is meant to be informal, I also want to keep things a bit qualitatively, and so I'm going to start with a very qualitative, robust picture of maybe the kind of ideas that we're going to be addressing here today. So let's get started. We've been throughout the last 3 weeks talking a lot about different scales and how gravity can be relevant or not, from all the way from being non-perturbative at the Planck scale, and perhaps now today discussing also implications in cosmology. So here I have a very qualitative description of what I call flat geometry of scales. It's a log 10 plot of numerous scales of the universe divided by the Planck scale. So 0, we are all the way to the Planck scale, and at 6 to 1, we're the size of the Hubble patch of observable universe. And you have in between, you have at 15, so 15 orders of magnitude higher than the Planck scale, we have the scales which are probed at CERN. 2 scales higher up, you have the electroweak scale, then you have the QCD scale, all the way to when you're 25, you're already around atoms. And then you have chemistry between atoms, all the way to us at 35 orders of magnitude greater than Planck scale. Then at 41, you have stellar mass black holes. And right after, you have typical size of the stars, the size of our sun. At 48, you have supermassive black holes. 55, the size of our galaxy, more or less. 57, cluster of galaxies. And 61, more or less, the typical size of our universe. And within this idea of flat geometry of scales, we can think of EFTs. We can think that whatever quantum gravity is going to be maybe relevant at the very short scales, beyond the scales that we can currently probe at CERN. And from that perspective, one could say, well, it would be absurd to ask someone to find QCD from tables and chairs, or to use QCD to explain what's happening in tables and chairs. But somehow, non-perturbative quantum gravity resting maybe around 0 on this plot should somehow be relevant at higher scales, and if so, how and why, right? So this is the qualitative picture of EFT and the separation of scales that somehow will prevent us from maybe probing quantum gravity in scales much higher than the Planck scale. Now the question is, how can we go beyond this picture, right? And what would happen? Before we talk about that, so within this EFT framework, of course, we expect that somehow there will be a final theory at some point that we can use to arguably, in principle, maybe not in practice, to explain everything that we observe in the universe. Currently, we are not there yet, but we have some theories. And we have, for instance, the standard model of particle physics that works really well, all the way from the scales probed at CERN, all the way to really at the interface where we start talking about chemistry. See that we stopped more or less there. This is more or less in this plot around 30. because that's more or less when you start probing with another force beyond the one that we see in standard model particle physics. And this is a scale where general relativity, or in that particular context, 1/r² gravitational forces are also present. And so, of course, that's not part of the standard model. And then we have the whole range in which GR as a classical theory makes sense. And that's why I also have included the green light for general relativity in the context of black holes. And I have this more shaded green higher up when you approach astrophysical scales, because we have things such as dark matter and dark energy that perhaps will be the case. We've seen this morning that maybe general relativity is not really the correct theory that we should be considering. Now, in the last few years, Frank Wilczek decided to call both the standard model particle physics together with GR the core theory. And then arguably, we could push the core theory all the way to higher scales, maybe close to the Planck scale. In fact, if you open Lukhanov's book, he's going to say that there is no reason to expect that there is any non-perturbative quantum gravitational effects all the way to the Planck, up to the Planck scale. Only then that would be relevant. But then you see that I have now the shaded area coming up earlier than just in GR, because of course, once you have black holes and you want to give a quantum treatment of black holes, we have things such as the black hole information paradox. So there is some tension when you bring together standard model and general relativity. Now the question is, where is quantum gravity in this particular diagram, right? So we know that quantum gravity should be somehow relevant non-perturbatively all the way to the bottom of this plot. And the question is, could maybe quantum gravity, if you go beyond this EFT framework, play a role around when you think about black holes? As we know, some people have hopes that because of the black hole information paradox, quantum gravity could be very important. And maybe all the way to the largest scales of the universe when you try to explain, for instance, dark energy or get rid of the cosmological constant problem, for instance. So in that context, we could somehow, in a very qualitative way, think that the geometry of scales is actually not really flat, but somehow is curved to some extent. And so we came across a UV-IR mixing the last few weeks of the workshop, which would maybe somehow relate those different scales across the universe, from the very small to the very large. And maybe actually what's happening at those scales that we cannot probe at CERN have something to do also with very large scales in the universe. We're going to probably hear more about that today. Another idea is that actually the geometry of scales is somehow extended. So in the context of string theory, for instance, there is a pivotal scale, which is a string scale. And once you go beyond that, some models, including models that people have worked on here, extend those scales all the way to another, you could imagine another dimension in that case, and that actually is made rigorous in the context of string theory, in which suddenly you go to physical scales that are bounced around this pivotal scale. But also in the context of bouncing cosmologies, there are theories that prevent you from approach all the way to the Planck scale. And 2 weeks ago, we heard from Neil Turok, about his model, in which there's also this kind of mirroring in the way that the universe is somehow created. There's also the notion of space-time emergence, that actually fundamentally, those scales, they are all in the context of field theory. But perhaps if you go further, what we really have is just underlying quantum mechanical theory in which all these notions of different scales, they are just effective. We're going to hear more about that throughout this week as well. And just one remark is that if this is true, then there is also the challenge of explaining how those scales come to be. Because obviously the idea of separation of scales might not be inherently present in your underlying quantum mechanical description. And the last one I just called, between scare quotes, fractal geometry of scales, but the idea is just to say that cosmology also instantiates another way in which these geometry of scales might be not as naive or simple as we'd like to be. Because in cosmology, through the expansion of the universe, those physical scales have been zoomed out or blown out to the proportion of the whole universe. And so arguably, to some extent, it could be that across all the different scales that we have access in the universe, to some extent, we are, one way or another, probing the scales that once were deeply connected or deeply present or within the Planck region. Or perhaps not. And I'm pretty sure they're going to hear some positions here that are going to say that this is one of the criteria that should be used to tell us if the scale that we do observe nowadays in the universe had anything to do with the scale that would be associated with the Planck regime. Anyway, so this is just very qualitatively, just to get us started up. And then to end, I also sent these slides some questions that they posed to the panelists for them to also have some initial thoughts. And here are a list of questions that perhaps we're going to be addressing or discussing today. So the first one is, does it make sense to talk about the universe as a quantum object? We had a talk this morning in which that was one of the topics of discussion, and we think of the universe as a full quantum object with a full Hilbert space and a wave function associated with the universe as a whole. Now, in the context of space-time being emergent, would there be any particular cosmological signatures that would be expected if that was the case, that wouldn't expect in other particular approaches? If there would be some convincing cosmological signatures of the quantum nature of gravity. Nowadays, there is a lot of discussion about the quantum nature of gravity in the context of tabletop experiments. But I was also wondering if maybe there is something that can be said in the context of cosmology that maybe we haven't talked about so far. In the context of primordial fluctuations, can they help us understand or probe past quantum gravity and different models? And if so, how? What quantum gravity effects might have been zoomed out to the large scales of the universe? So if indeed quantum gravity, all the fluctuations we have in the universe somehow had anything to do with the Planck regime, are those signatures still present, or they are completely diluted away? How could quantum gravity be related, if at all, with dark matter? So we know that different quantum gravity theories might also introduce some different particle candidates that might be able to explain dark matter. And similarly, can use quantum gravity to help us understand dark energy or to get rid of the cosmological constant problem somehow. And perhaps that UVR mixing that we mentioned before could be one of the possible solutions. Again, can we use cosmology as a whole to test and rule out the different candidates of a theory of quantum gravity? And if so, how? And finally, if this EXT paradigm that I mentioned in the beginning is broken in the context of quantum gravity, what should we do? How should we think about that? So this is the introduction to the panel discussion today. And now I invite, by order of first name, first Alberto, to give your first remarks. It can be 3 slides or on the whiteboard.
Okay, so first a comment about the first point. Does it make sense to talk about the universe as a quantum object? So to me, since life is impossible in the early universe, one has to revisit a little bit the concept of observers and observables in quantum cosmology, because of course we cannot observe everything if observers are not possible. So the concept of observables has to be restricted to something that is observable at late time. So for example, if something is supposed to be to predict values that are real for observations, this must be true only for observables that leads to observations at late time. Okay, so this is the first remark. And then I have also prepared some little explanations of what the theory I've been working on predicts for the large distance ground state of the theory. So maybe I can write it in the blackboard. So basically, using this perturbative and background independent formulation that I've discussed this morning, one can obtain a formula for the wave function of the vacuum, means the psi zero, the wave function corresponding to the minimal value of the eigenvalues of the Hamiltonian. If you look at this,
So could you write it a bit bigger?
First write it down and then explain what.
Can you write it a bit bigger, please?
A little bit bigger.
Yeah, because the camera doesn't.
Okay. So I will first write it down and then explain what the symbols are. So these QI, QF are being defined during my talk. And this H hat represents the quantum Hamiltonian. Psi zero, as I said, is the wave function of the vacuum. And this N0 is some QF independent normalization constant that is physically relevant. So this form basically is equal to the compass conjugate of psi zero at Qi. And this eta means that I'm switching the sign of all these Dirac-Pauli variables that I've introduced. And here E0 is the energy of the vacuum. That means the minimal eigenvalue of H hat. And it can be computed with the following formula. Now the path integral that I show you. So this is everything is Euclidean, complex imaginary time. So this transition amplitude can be computed with the path integral I showed you before. Path integral of the matrix with the initial and final values of the canonical coordinates fixed, the genetic gauge F, of the usual e to the minus Euclidean action divided by h bar. So this ground state can be computed once you give a meaning to this. Of course, it requires some space-time discretization, but you have a formula for it. And these wave functionals, like the ground state wave functional, satisfy the Wheeler-DeWitt, some sort of Wheeler-DeWitt equation that just looks like this in this notation. Now, from this formula, you can also show that the wave functionals with a smaller e, smaller value of the eigenvalue of h hat in the large distance limit are those that somewhat are picked around configurations for which the Euclidean action is more. So this is connected probably to this finite action principle that Lenners and Kellogg proposed in these papers. So let's take a state psi that is an eigenstate of h hat with eigenvalue e. And then, of course, we have that QF eta times e to the minus tau f minus tau I, some initial and final Euclidean time h hat over h bar, as this state psi is equal, since this state psi is an eigenstate of h hat with eigenvalue e to the minus tau f minus tau I E divided by h bar qf eta psi. Okay. Okay, so on the other hand, by using the completeness relation, one can, from this result, one can write that the integral over dqi, this has to be thought of as a path integral, actually, because it's an integral over initial configurations for the canonical coordinates, that are fields. This has to be thought of as a path integral. Qf eta e to the minus tau f minus tau I h hat h bar times qi eta psi is equal to the same thing, because it's equal to this. Here I'm inserting the completeness relation that in this theory is not just integral over dqi of qi, but it is integral over qi of qi eta. Because in the case of the applied variables, this is the case. And now we can multiply both this and this, that should be equal, by psi qf eta integrating over qf. If you do that, I get integral over dqi, this integral, dqf, and I'm putting psi qf eta here. And I have this, qf eta to the minus tau f minus tau I h hat over h bar, qi eta psi, and then I do the same operation here. So I'm multiplying by psi qf eta, which is the complex conjugate of qf eta psi, and then I'm integrating over qf. Okay, so what I get by doing these operations here, I get the integral over qf of this inner product absolute value squared. But this can be put equal to 1 by a normalization choice of the state, just like in normal quantum mechanics. So by a physically irrelevant normalization choice, I get that this is equal to e to the minus tau f minus tau I e over h bar. Okay, so if I now remember what this is, now I can call this tau f minus tau I can just call it tau. I have a path integral expression for this object. So you see that eigenvalues that have the minimal values of E, those that are relevant at large distances, corresponds somehow to wave functionals that are picked around configurations that minimize the Euclidean action by this formula. Because this, so if this is true, then this quantity here is minimized, and this corresponds to the value. Sorry, this quantity here is maximized, and this corresponds to the value of E that are minimized. So from here you get a connection between the size of the eigenvalues and the configurations that maximize the wave functions and also minimize the Euclidean action. Yes, yes.
Oh, I have a minute left.
Yeah, it's over.
Yeah, okay, perfect.
Okay.
Okay, thanks. You can go choose the whiteboard.
Yes. Okay.
Well, I'm much less well prepared than everybody else, so mine's more of a discussion. But I want to address two of the questions, which I think are almost like the same question, of dark matter and dark energy. I find it incredibly embarrassing that 95% of our universe, of the energy density in our universe, is dark. What does that mean? Well, it's 25% approximately dark matter. So that's wrong for a start. 70% dark energy. And we have this habit, we don't understand something, it doesn't interact with photons, it's dark. I understand where dark comes from. In my humble opinion, there is a big difference between dark matter and dark energy. Dark matter we see in galactic rotation curves. There is much more matter in a galaxy than is luminous. We feel it in our galactic halo, and we've seen it in the bullet cluster where the cluster goes through. What the hell it is, I haven't a clue. We switched the LHC on, we saw the Higgs, and that's a great success, and we saw nothing else. No evidence of any so-called dark matter particles, which could be the supersymmetric partner of ordinary matter. There's no evidence for supersymmetry up to the maximum scale that the LHC gets to. It could be primordial black holes, and later in the week, Francesca's giving a really interesting talk, which, well, at least the abstract looked really interesting. So it could be something along the lines of primordial black holes. My understanding is that they don't give the whole of the dark matter, but I don't know. I'm not an expert on that. Dark energy is much more mysterious. A long time ago, people came up with ideas of quintessence, and some of us, actually 20 years ago now, thought of modified gravity, scalar tensor theories, string theories, and all that. Try as hard as we might, we haven't been able to really get the dark energy scale out. We essentially put it in, and you've got constraints on these models. But I think it's very, very different. And I strongly suspect that it's a hint that we're doing something wrong. What we've been doing, well, we have the two big tenets of 20th century physics. We've got GR and quantum theory, quantum mechanics. What we did with quantum theories of quantum QFT, what we did, we took electromagnetism, and we went to QED. Great. Then we've gone to QCD and the standard model. What we've attempted to do is to do exactly the same here and go to quantum gravity. And we've run into all those problems. It's not renormalizable. We don't really know what we're doing. And I strongly suspect, because what we really do now to get predictions in cosmology, we take GR, we take the Einstein-Hilbert action, and we stuff the matter in. Perhaps it's the inflaton. We've got the standard model particles. That gives us the reheating of the universe if we've got inflation. But we're always treating this semi-classically. The fluctuations are classical. The fluctuations are quantum mechanical. But we are treating this part, the Einstein-Hilbert action, classically. And there's something crazy about that. It's wrong. And I strongly suspect that this is a hint of new physics, of a new way of doing things, a new way of coming together. I don't know what it is. If I had a clue what to do, I would tell you in the hope that you young people would go away and do the calculations that I personally am too old to do. I don't, people. So this, I think, is the biggest clue we have. I hope that sort of answers things. I tried to think if there's anything else that could be a clue that we don't really understand what we're doing. People bang on a bit about the Hubble tension, and I suspect there's something there in the astrophysics rather than fundamental. I might be wrong there, but I don't get too het up about that one. Are there anything else I can say? I don't think there is really, but I think this is a great question. Could quantum gravity help us understand dark energy or the cosmological constant problem? Yes, I'm pretty sure it could. And you're probably quantizing it in the wrong way. You know, we need to do something different. I don't really know if it's R squared. Probably not. That's probably too simple. I don't know. I think that's probably all I've really got to say.
Thank you.
Have your slides? Sure. Please.
So I wanted to have just make a couple of remarks on themes rather than results. Along the lines of asymptotic safety and possibly, well, here's some of the themes that I wanted to talk about. One is a question of whether quantum corrections can actually inform the discussion about the very early universe, in particular, whether it can give some meat to Penrose's proposals about the boundary conditions of the early universe. Another theme would in fact involve the Hartle and Hawking no boundary proposal, and also what you have to do in order to try to put some meat on that with the from the Feynman path integral point of view, which will require you to learn how to integrate over complex metrics. In the process, in fact, basically both of these, there's a possibility that particularly from a string theory point of view, there's this notion of the landscape, which is far too rich a family of scenarios, as they would say in Hollywood. And is it possible that cosmology can actually filter that and tell us, at least with some boundaries, where we might live? So just some ideas. This is going to be in the context of the what's called quadratic gravity now, the renormalizable gravity. Weil squared, R squared, fourth order terms, and the Einstein-Hilbert term and the cosmological constant. Again, I don't want to go through the details. This is really just to try to name some of the themes. And this is following Niedermeyer's approach on asymptotic safety, which uses the renormalizability of this theory so that you more or less know where you are, as opposed to just considering the entire kitchen sink of all possible operators. These are the ones that are going to be renormalized, and so you can actually talk about renormalization group evolution. So that's the story of asymptotic safety. These are the original Avramidy and Barvinsky version of the renormalization group equations, and there is recent discussion that we just heard this morning by Donahue, Roberto Spicacci, and others and students on whether this is the appropriate set of renormalization group equations. However, I will say that caveat applies mainly to the R squared term and the issue of the scalar, which is a nice scalar anyway. You will love it whether it's asymptotically free or not. When you're wanting it to be asymptotically free without being a tachyon has a lot to do with whether you want to be greedy and say, let's also do inflation in this context. But I don't want to go there. I really want to talk more about what this could say on the boundary conditions of the universe. So the couplings run. Asymptotic safety means, of course, if it's asymptotically free in the two higher dimensional terms, those couplings will go to zero, but then you also have the cosmological constant and Newton's constant. And so in that sense, there is an asymptotically safe scenario. Okay, now we're going to adopt a certain principle called the finite Euclidean action principle. We've also heard some mention of that earlier today, that the quantum action in the Feynman path integral should, in fact, not blow up, right? Basically, the integral should be a well-defined thing, and that requires that the time integral be convergent, in particular as one approaches zero volume at t equals 0. This is different from an initial proposal by John Barrow. Sadly, it's one of our colleagues is gone, but Barrow and Tipler proposed a finite Euclidean action principle over all times. This is different. It's from the beginning to now, rather than the beginning to the infinite future. Now, that is the scenario. We adopt this and see whether you can learn something. So in order to try to test this out, you need a playground. And so together with Jean-Luc Lenners, we looked at the family of Bianchi-9 metrics. Okay, again, I'm not going to go through the details of this, but you can discuss, for example, the issue of anisotropy in this context by substituting this family of metrics with its parameters into the action, and now see whether the finite Euclidean action principle tells you anything about it. Going through the discussion in Einstein's theory, you find the answer is no. Einstein's theory is happy. You don't have any particular constraint on the parameters of Bianchi-9, which is allowed anisotropies. So basically, from Einstein's theory, it's cool whether you have an anisotropic universe or not. But when you include the quadratic curvature terms, the story changes. And that's where you go through a whole series of discussions with the various BKL type T dependencies. And if you, as you go through the analysis, again, you see here in Einstein's theory, you basically don't obtain a constraint. You do when you include the quadratic curvature terms. And in fact, it basically leads to restrictions on scalings, and they filter out the universes that start out anisotropically. So the quantum corrections actually can be telling you something about the boundary conditions on the early universe subject to this finite Euclidean action principle. That's all I really wanted to say about this, that quantum, the effective theory of quantum gravity, it could be that it's telling you something about the very beginning of the universe. And in fact, of course, that should make Roger Penrose happy. Similarly, for inhomogeneities, with the Lemaitre-Tolman bond dimetric, you also go through the same sort of analysis. And again, you don't learn anything in Einstein's theory, but you do in the quadratic, including the quadratic curvatures. Okay, so that was what I wanted to say about that. That's a possible implication of quantum corrections for the very early universe. Now, if we go way, way back to the very beginning, we can investigate whether the Hartle and Hawking idea of the no boundary proposal actually can also be related to some of this discussion. So they did something rather strange. Of course, it was Cambridge, right? And I know Anne is part of that crowd, but in Cambridge for a long time, everybody was doing only Euclidean quantum gravity, whereas I like to digest my lunch and I require inconvenient time. So how do you get from there to here? Well, Hartle and Hawking gave you a proposal, first of all, that they said the wave function of the universe should be calculated by a path integral. defined by a sum over compact regular Euclidean metrics, okay? And from a no boundary initial condition to final condition. Well, what's final condition? There has to be some intermediate time when you turn on the Minkowskian time. And their proposal was basically to glue things together. If you took complex de Sitter, i.e. sphere, or sphere, and around its equator, you can actually glue it on to a Minkowski signature type of de Sitter. And that's just because their names are Hartle and Hawking, and they said, let's do it. Okay, so it matches, and there's a decade of generation of discussion of this sort of thing, of just gluing it. Now that obviously isn't very satisfying, but so you can ask, can you actually provide a better context for all of this? Well, this is something that's actually been discussed increasingly recently. In order to try to make more sense of this, you have to consider the possibility, consider formalisms in two times, an imaginary time and a Euclidean and a real time. In other words, you're doing path integral over a higher dimensional complex spacetime with time as complex. This allows you to incorporate both the Euclidean beginning and eventually what you need for digesting your lunch. Now, how are you going to do path integrals in this context becomes the question. So Kontsevich and Siegel proposed a certain, I'm not going to go through the details of this, but just again, you the flavor of it. They formulate it this way, and it's clearly not totally satisfactory, but this is just another to get going. A metric is allowable if you can do quantum field theory on it, in the sense that the path integral of the quantum field theory converges for all NP forms. It's also in the context of supergravity, superstring theories. There are lots of higher rank generalizations of Maxwell's theory of antisymmetric tensor gauge fields. Okay, so a series of papers here. Lucas, Orkin, Kontsevich, Siegel, Witten, and Jean-Luc Lenners has been working on this quite a lot. Okay, so then there's given that rules of the game, a metric is allowable if a generic quantum field theory can be defined on it, such as path integral converges for P-form actions. And then you get a sort of restriction on the allowable families of metrics, which now you're going to do path integrals over the metrics too, but you're going to limit the path integral so it makes sense. And you end up with this sort of constraint on the allowable metrics. And you end up with this. Again, obviously, not what you do path integrals, you're going to use Cephas descent technology as the settle points. That's until you get quantum computers or whatever else we're going to have for future technology. That's pretty much what you're limited to. And in order to try this out, together with Jean-Luc Lenners and my student Raheem Lung, we again, because I typically start in higher dimensions, right? Let's look at an 8-dimensional model of Starobinski's sort with R and R to the 4th, and also a 4-form field strength squared. Now, one of the things that's new about this is it allows you to consider no boundary type proposals where you actually turn on some flux for the 4-form, and you get a family in the end of effective potentials depending upon the amount of flux that you turn on. There's the n equals 11, 13, 17, and so forth. So that's the game we were playing. And again, now considering integrations over complex metrics with the Kontsevich, Siegel, et cetera, rules. Now, because this is in 8 dimensions, we want to end up down here in 4 dimensions. We're going to dimensionally reduce on the sphere. When you do that, you generate out of the metric, you generate scalar fields and vector fields and so forth. So the scalar comes out, and now you can put things into Einstein frame by making a Weyl transformation after the dimensional reduction. And so you end up with gravity, a scalar, and a 4-form. And now you go through the discussion of Steepest descents on saddle points and so forth. depending on the various parameters. Okay, so what these plots show you are, so the imaginary part of A is the cosmological scale factor, phi is that scalar field. And what you want to see is if you start here basically at the bottom where everything is Euclidean, that's where you have purely dependence on the Euclidean imaginary time. You would like it to evolve into a situation where time has become effectively Minkowskian. And that actually happens for a certain range of these parameters. So the South Pole is the origin of the Hartle-Hawking beginning of the universe. The horizontal axis corresponds to Euclidean time. The vertical axis is Lorentzian time. And the darker colors indicate smaller imaginary values. So the black lines show basically the locus of real values. Now, by the way, over here you can see what Hartle and Hawking, because they are Hartle and Hawking, this dotted line is actually their transition from purely Euclidean to purely Lorentzian, because that's what they said to do by gluing it together at the waist. But you see, what this is actually showing you is it's possible to have a path integral formulation which makes that happen naturally. My final point is that this depends upon some of the parameters that you put in your choices of how much flux and so forth, and you end up with regions where it doesn't work, where there's no potential, regions where it works, where you have a no boundary solution and stable internal dimensions, or regions where there's no boundary solution, but the extra dimensions, remember we had this force field that we were reducing on, and that can blow up. So actually, within this context, it's possible that there's a selection principle that provides some probability distribution on solutions, and possibly giving a filter on the landscape. So that's what I wanted to do, is just sound some themes here about ways that quantum effects can, from a cosmological perspective, can have a direct relation to some of the key issues that we need to discuss in this subject. So thanks for your attention. You what? You know how to drive forward, backwards.
Okay, oops. I welcome again. Organizers, it's quite learning. I was not fully aware of this recent results, which are that fellow Stelle has provided. So let me just jump through this, that are very specific questions to something that I pick up as an inspiration from the book of Ryan and Shapley, where they have this sort of a roadmap from chapter to chapter. So as far as quantum cosmology goes, I've been interested, and I think it's still interesting for anyone to consider old problems that are there, and perhaps to try new tools and new aspects that may uncover some aspects that may be useful, and also address the questions that the chairman has here. So let me perhaps start here and say that maybe this should be the last diagram, but let me go, for example, to illustrate to the boundary conditions. Strangely enough, I see the red dot on the palm of my hand, but the red dot is somewhat swallowed up in the screen. The aspects of having boundary condition, namely the Hartle-Hawking, there is a typo there, but it's worthy to mention that even for the most simple case of Friedman model in the scalar field, and when you take the slicing of the S4 spin at the lower bottom, so when the theta is the less than half, you don't find for the path integral a straightforward choice to calculate the saddle point. So when you go and consider, say, the more than half, you can still got a wave function that provides enough quality, meaning results that satisfy what we would expect. This gets worse. This, I don't know if I can point there, but maybe I should join the one. But the point is, when you are considering this degeneracy, if you now go like Halliwell and Yormoloko has done and consider anisotropic cases, the way to choose using, say, the contour for your path integral goes really messy. So we put some criteria. Jonathan Halliwell has put this in a paper, how to do the contour correctly. So this is 1990, something like that. And he says one of the aspects is that the square root of the metric must be positive, and also you must have that the contour from the incurved space that you retrieve from there must be such and such. So it is like it's not enough. The no boundary doesn't give you a safe choice, a comfortable choice for the contour of the path integral. So there is this degeneracy. So remarkably, as I was mentioning this morning, Linners and others came up with the use of this mathematical tool called the Fischer-Lefschetz. So they are using not the Euclidean path integral, but they say we are going to use a Lorentzian path integral with oscillates, and we are going to show that it actually converges and it's safe to use. So this was like an immense result at the time. As I said, papers come up on the archive by Linners and group, and suddenly by Halliwell and others, papers subsequently came up next week or 2 weeks after. It was really intense. The point that I make this connection here is that when you try to identify the Lifshitz symbols or symbols that are, say, the main contribution, the dominant contribution to your path integral that gives you physical results, they are in fact ground states or solutions of your Morse function, and they are, as Witten have shown, they are ground states of an n equals to supersymmetry. So there is something there. So what I'm trying to say is that there are still some things, some issues that are worthy to look at, even if you look at papers from the early 90s in cosmology. So these masters and old masters were looking at something that, and now others are there. The other aspect I would like to bring here is, which in my view is also worthy, is that the Witt conjecture. So Bryce DeWitt back in 1967 or 68 in his paper said, no boundary conditions, constraints are everything. The algebra should give you the answer. So then he sort of put there, okay, it's the wave function is zero and the derivative is zero near the singularity. So this is called now the Robin boundary condition, which is something comes when Linners do something to get some suitable and comfortable embrace with the no bound. So there is something that is worthy to discuss. My point here is that when you consider the algebra of constraints of your model, and this must be like a suitable, really fine toy model where you have more symmetry than just the obvious, say, duality and say something like that, then you use this algebra of constraints, which we call the hidden symmetries, and you can show that the results provide you that the solution of the wave function in this case is something that satisfies the DeWitt conjecture. Again, it is something that has not been done. Is how can you put in these hidden symmetries supersymmetry or n equals to supersymmetry? This has not been done, and this is something that, in my opinion, is worthy to look at. Sorry, not here. So, another aspect
that I would like to mention is that about the chaos theory and quantum chaos. So maybe because it was something new at the time, I remember that talk by Neil Cornish, and I don't remember if it was Paul Scheller or not, it was 1997. And they were actually showing that when you go study and discuss the WKB approximation, you get situations where the integrability and the WKB may not be good enough. So the no boundary, which is a solution which depends on a semi-classical approximation and the WKB fixing the results, may just be almost a zero measure on the solution theory, and the other are just something that has been chaotic. So if you use chaos theory with quantum mechanics, which is something more than a problem, it's not defined. So this is something that goes through some groups and knowledge is not properly defined. Can you use it for quantum cosmology? To my knowledge, no one has the answer. So there are some interesting aspects called the trace formula by Gutzwiller and others, and then results by Michael Berry, I think it's the man that is in Bristol, which he called quantum chaology. How do you get chaos classically from a quantum mechanics? Because quantum mechanics is Schrödinger, is linear, and chaos is non-linear. How do you retrieve something non-linear there? So this is something that when you go back to quantum cosmology and you need some way that to get to the classical universe, you cannot ignore. So as I said, there are questions that they are still remaining, and I think if they are worthy to consider. Now, to the other side of this picture. So this is what, for example, people like Klaus Kiefer has been doing. It's not actually expansion. This is X-even. So this is a terrible faux pas of when sometimes something is missing. It's like that cartoon in Australia when they say, beware crocodiles, do not swim here. And the fact that you put a dot or not, it's life-changing or so. So you understand. So this is, S expansion means you are expanding in powers of the Planck mass. So it's like your action. And what has been done by the school of Klaus Kiefer and so on is you expand your wave function, starting from a semi-classical, just the WQV form, and you get corrections to your Schrödinger equation, quantum gravitational correction to your Schrödinger equation. There are two types. Both of them can lead to enormous problems, say, of non-utility. So this already says that when you are doing quantum cosmology and you are trying to get a classical universe, 1 minute, I'll speed it up, and you get a classical universe, you don't find comfortable enough procedures that will allow you to say, I'm safe. You are not safe. So if you take the fact that you get orthogonal corrections, so this means orthogonal to the hypersurfaces in superspace, even then the quantum gravitational correction to your Schrödinger equation may give you problem because some terms either you correct or not. But if you consider the tangential corrections, you are breaking WKB, you are going away from those trajectories in superspace, and you don't know what happened. So this is something that has not been done. Both of them, chaos or that means to a rupture of WKB. So it's not good enough. And just to conclude, I'll just finally, in a couple of seconds, I think it's worth it if people consider using fractional calculus in quantum cosmology like people have been doing in quantum mechanics as well. It may be silly, it may not be worthy, but it's fun. So and sometimes you do some back of the envelope calculation and you find something that has been worthy. And they have been doing it in other fields of physics. Why not here? The other aspect is consider quantum groups, so non-commutativity. Maybe that's something that when you consider general relativity or beyond general relativity, you can consider, and you really get new results in terms of the solution. Maybe just to summarize and to conclude, it is interesting that when you use fractional calculus and you get your solutions, and you apply this to a black hole, to the entropy of a black hole, you get results that you can associate with the solids and barrel entropy. So maybe this is just coincidence. Maybe this is just the results of doing some fun with your calculation and mean nothing. But these are just aspects that I was asked to provide regarding quantum cosmology that perhaps go a little bit beyond the usual setting, but I hope they are motivating enough for eager young minds. Thank you.
Wait, can I interrupt for a second?
Maybe after.
No, I would like to say that now because I get very confused.
Sure.
I followed this very nice list of questions which you have said, and I'm afraid in the presentations I hear so far, apart the general remark from nobody had tried to give anything in these questions. Everybody is waiting. Thank you, because I'm completely lost. Everybody presents literature in your work which has nothing to do with the nice questions. So either I'm missing something, I apologize, and then please tell me what I missed. Otherwise, I don't know what's going on.
I'll try to satisfy you there.
Thank you very much.
When I get the answer to the first question,
Let me
heard about
let me
Completely out of the
Let me,
context of the discussion in general. I mean, I don't think it's only my feeling.
good. Okay, so let me go to the list of questions which
Thank you.
you saw. In fact, there are so many good questions that it doesn't even fit on one slide. So it's 1.5 slides. Okay, so now what I did is I slightly reoriented the order of the questions. And the first question which I want to address is, if quantum gravity breaks the effective field paradigm, what should we do? So I'm here to be provocative. So my answer is that the effective field theory paradigm is definitely inapplicable in cosmology and also in quantum gravity on small scales and in the early universe. Now, what are the arguments? Argument number one, and I'll expand on that in my talk tomorrow morning, it's a trans-Planckian censorship criterion. The argument two is a very nice paper which just appeared by a collaborator of mine, Simon Carl-Hewitt and Guilherme, which is a bottom-up analysis starting from graviton scattering amplitudes. It argues that effective field theory inevitably breaks down at the Planck scale. In fact, the conventional effective field theory breaks down even at the lower scale, namely the species scale. Okay, so this is my point of view on this. So quantum gravity definitely breaks the effective field theory paradigm. What should we do? Okay, what should we do? This is our job, and I will present a proposal tomorrow. Okay, now, question number two in my list of your questions. If space-time is emergent, what type of cosmological signatures could we expect? So I believe that space-time is emergent, and again, I'll present the model tomorrow. And I think quite convincingly that these signatures will be imprinted in cosmological perturbations and gravitational waves. And I think you would definitely agree with that now. Okay, so now another question is, what would be a convincing cosmological signature of the quantum nature of gravity? Okay, so with current observations, we do not have any evidence. Now, if you measure the spectrum of primordial gravitational waves and you find a blue tensor tilt, which is in agreement with this consistency relation, tensor tilt equals 1 minus ms. We know what ns is, so it means tensor tilt 0.04. Then I would say we have evidence for quantum gravity. Now, we have evidence for a particular approach to quantum gravity. This is what will emerge, what emerged from string gas cosmology, and it is emerging from our matrix cosmology. Now, other people working on other approaches to quantum gravity should also be able to come up with a prediction like this for cosmological observations. Okay, because we want to test quantum gravity. Maybe the approach that I'm working on is wrong. So the universe is expanding, and even if quantum gravity only works on very small length scales, the expansion of the universe will zoom out the effects and will make them visible. So quantum gravity is going to be crucial to determine the initial conditions for fluctuations at the beginning of the standard Big Bang cosmology epoch. So now, no answer to that. I agree with Anne's prejudice that dark matter is probably matter. Now, does it make sense to talk about the universe as a quantum object? I don't have so firm opinions about that. I will, since I'm not a quantum gravity expert, I will say yes with a very soft voice, because I don't think otherwise we can have a unified quantum theory of all forces consistent with the Franzmann censorship conjecture. But the more important question which I want to turn to is this one. How could a theory of quantum gravity help us understand the dark energy and or cosmological constant problem? And these are two independent questions. And I'll first talk about the cosmological constant problem. So I claim, and I'll try to justify it tomorrow, that the quantum aspect of the cosmological constant problem is an artifact of using effective field theory in a domain where it is inapplicable. It comes from quantizing harmonic oscillators. If that's not what quantum gravity does, the cosmological constant problem disappears. And now the much more interesting point, and there I come back to what you said, Anne, dark energy. So I think this is going to be the key. So I think this is where quantum gravity should see. We want to understand dark energy. And I actually think that the quantum gravity model, which successfully explains dark energy without fine-tuning, that's going to be the right quantum theory of gravity. And I think what you said, infrared ultraviolet correspondence, I completely agree with. Okay, good. Hopefully different quantum gravity models will make different predictions for cosmological observations, so we can test that. Now, just a little bit of background. So the Transplanckian censorship criterion, not conjecture, criterion. It has nothing to do specifically with string theory. It's much more general. So this is a space-time diagram of inflation. Vertical axis time, horizontal axis space, and times between Ti and Tr, that's inflation. Inflation, exponential expansion of space, scales that we observe today, exponentially expanding, they come from the zone of ignorance, lengths smaller than a Planck length. So this is old stuff. What is new stuff is turning this into a criterion or conjecture. The correct quantum theory of gravity should not allow this space-time diagram to occur. Scales which are initially sub-Planckian should be hidden forever from the classical regime, which is exactly this equation in the box. Okay, now this effectively means, as I'll show you tomorrow, that standard slow roll inflation, independent or not, whether it's given by scalar field, is simply out. So, okay, I'll skip that. So this is the condition for inflation to be successful, inflation. And you see that the Transplanckian censorship, which actually gives rise to an upper bound on the energy scale of inflation, which basically means it requires extreme fine-tuning. Okay. TCC also means that dark energy. We know what dark energy is not. It's not a cosmological constant. And I agree with Anne that it's not just simple quintessence. Okay, so rest in peace, the inflationary scenario of structural formation. Go on to something better, for example, a bouncing cosmology. So here, pre-bounce, post-bounce, some new physics, quantum gravity, or the emergent universe, an emergent phase, which might be modelable by constant scale factor, phase transition, standard Big Bang cosmology. Quantum gravity regime sets the initial conditions for fluctuation. So, okay, so hopefully I've been provocative and address these questions, Larry. So
I'm satisfied.
thanks.
I have a question to you. I don't know whether
Yeah,
questions.
now we're open for everyone, so please go ahead.
Yeah, and so when you discuss at the end for the conditions for inflation, so let's say, but because before we discussed a bit, if I don't have inflation and I find another mechanism for the perturbations which I need, then what can you say for these constraints there?
What you mean? Constant
Yeah. Then I don't need any. I don't need.
In bouncing cosmologies and in emergent cosmologies, scales that we observe today are always consistent with the transquantum.
Yeah. So
the transquantum censorship
is another thing.
Does not constrain bouncing cosmologies and does not constrain emergent cosmologies.
Okay. So then
it only constrains poor
inflation. So I cannot constrain. Okay, fine.
Okay, so now let's try to follow the scheme. Full hand if you have a topic you're going to propose. Finger if you want to follow up or comment on that. Of course, we're not super strict, so they're going to be back and forth. But just so we can be able to respectful and I can keep track of who is in order. I think you had one?
Well,
yeah.
I had a question. Can we say now that inflationary models are really worse than bouncing models?
Okay, so
yeah,
inflation based on effective field theory is inconsistent. But then notice inflation based on effective field.
Not inflation, the complete field.
Not necessarily. No, you have to present me a UV complete theory, and then I'll look into it.
Okay.
Yeah, I have a questions about this dark matter, dark energy. For dark energy, I fully agree that should be quantum gravity, could be quantum gravity. Now, when we talk for dark matter, then we should think that there are some modifications in the same way as this very ugly and physical Teller's model that come from some quantum gravity corrections that modify the action and could act in the same way like these extra fields that they try to solve the issue of dark matter. That's how we should see it.
Okay, so again, I'm not an expert on dark matter. I'm fairly conservative on dark matter. So the key challenge for anyone who wants to propose a gravitational explanation for dark matter is they have to explain the agreement between the amplitude of CMB anisotropies and the amplitude of the galaxy correlation function. Because if you just take standard GR and you eliminate dark matter, you get a disagreement by one order of magnitude.
Right. But the way that one should see it is what I tried to say before, some kind of extra terms that should come from a quantum gravity kind of proposal, in the same way like you have the extra scalar and vector part that go completely by hand put in the Teller's model. It should be some modification in the action that they should act in a corresponding way.
So see, I was very conservative in everything I said, but now I'm going to be conservative. I tend to prefer something like the axion.
Yeah, okay.
Yeah, but I don't have firm.
Yeah,
I don't have firm views on it.
Yeah, but then it's not really a quantum gravity.
That's right. So I would.
But I said that because it was in the list. If it's a quantum gravity, and for me up to now, from what circulates in the market, I would go to primordial black holes and actions. I think these are the two that win right now. But if we want to give a more fundamental thing, because primordial black holes could be, but action is again something that you put it a bit by hand. Then if I see it like a quantum gravity correction, then I would expect that I had some modification in my Einstein-Hilbert action that plays the role of the vector and scalar part that we put by hand in the Teller's model. I'm trying to see, because you seem that you agree that matter could be quantum gravity, so I'm trying to think how.
No, I would not bet on it. I would bet against it without matter.
Yeah, I would too. I
think, Anne, in your stuff, you mentioned that could be quantum gravity, the origin of dark matter. No? Okay.
No, dark energy.
Okay, only dark energy. Fine. Then I think we agree.
I think there's a big difference between dark matter and dark energy. in the way that galactic objects behave. We go all the way back to Vera Rubin and the way her rotation curves. There's more mass observation of the bullet cluster.
No, I agree for me as well.
I just can't see that could be a quantum gravity effect.
I agree with you.
And I agree with Robert that, you know, the two leading candidates have to be the axion or primordial black hole. And
no, I agree.
Or maybe
That
both.
matter could dark energy could be
Dark energy.
of hard time, yeah.
I think that must be our lack of understanding of fundamental physics,
Sorry,
of gravity.
what are the scalar and vector that you mentioned?
No, I'm just
What
saying,
were
you
you
know,
referring to?
it was this model MOND, which was an empirical model.
Yeah.
And then there was introduced the PEVES, like the relativistic kind of thing that can give it, which of course is ugly. And of course they have failed many times, but I was trying to see if it was of the quantum gravity or that's how I should see it. And just, I found it a bit unnatural, but I was trying, probably I misunderstood. I thought that we both meant that also dark matter could be a quantum one. Then we agree, that's fine.
Yeah. There was just to mention shortly that there was a proposal by Stefan Alexander, and it's a proposal that was originated with Liz Molin, in which they were considering a quantum equivalence principle that was in the context of the Chern-Simon theory for cosmology. And there was a claim in a series of papers that this could lead to a kind of dark matter effect that was compatible both at the scale of the early universe and on the galaxy scale. But this is, of course, my preference. You know, I come from the preference of regarding black holes, but this is still on the table so far as I know.
Well, first of all, I always have, when we have this kind of debate about dark matter, I always remember Leverrier in 1946 basically predicted where Neptune should be by the perturbation in the orbit of Uranus. And then there was a similar problem with the perihelion of Mercury. And he conjectured that there was a dark planet called Vulcano that they looked for, and this time dark matter didn't work. And it was actually a modified, an extension of Newtonian gravity that solved the problem, GR. So it seems to me that we are back to, you know, that kind of situation. We are debating which of the two approaches are there. My point of view is that with respect to dark matter, we have to be careful in a certain sense making this big division. Because you see, what is matter and what is gravity in gravitational theory is a matter of representation very often. It's very difficult to say, this is matter, this is gravity. You change representation, sometimes you mix things. Now, dark matter could be a form of matter, of course, but it has to be a very special one because it doesn't behave the same way in cosmology and at short scale, a small scale. I mean, we have to face the fact that in most of the astrophysics community, a lot of people start to be skeptical about cold dark matter at the level of galaxies. And not because they have a prejudice, but because simply under CDM has problems. I mean, CDM has problems at short scale. So it may be that it is a matter field, but it may be, for example, that is a minimally matter field. But then if it is a minimally coupled, is it matter or is it gravity? So, or if it's, you know, no minimal coupling, it's something that you can dynamically switch on. It doesn't need to be a fundamental theory, coming from a fundamental theory. I can tell you how. Imagine that dark matter forms large Bose-Einstein condensate in galactic halos. It will have a very long coherence length. It may have a very long coherence length. In that case, it may fill the curvature and couple to curvature in a very non-trivial way. I myself have worked on this kind of model. This is why I'm just putting it up. But I'm just saying, it's very difficult to say, it's surely matter, it's surely gravity. You have to be careful because matter and gravity have this bad habit to interplay, to mix very deeply.
And what you put on the left-hand side and the right-hand side of Einstein equation, you can put things on the right-hand side or left-hand side of Einstein equation.
Yeah, it's the number of degrees of freedom which is relevant, not the representation. You change representation, you can move things around. What is really fundamental is how many degrees of freedom you have your theory. At most, you can freeze them in some background, but Those are the
interactions between
the fundamental things, right? Once you give me the theory, the number of degrees of freedom, how you then reshuffle them in a different representation by different set of fields, that is another matter. I'm just saying that, you see, as a cautionary note, there are models where if you can start with the dark matter, called dark matter, then this dark matter can develop on minimal coupling at short scale and behave providing an effective geometry. I mean, you can really show that if you have a minimal coupling like Einstein tensor, nabla-Muffy, in the Jordan frame, you go in the Einstein frame, and this will be basically the stress energy tensor coupled to this formal geometry, which is the Einstein metric plus nabla-Muffy. So basically, you have a kind of modified gravity theory in that frame. You have to be careful in making, this it's A or B. There is a lot of gray zone in the description, and this is one of the problems with gravity. The degrees of freedom can always be reshuffled in a different way. You may have two theories that look completely different, then they are, as prediction goes, equivalent, because they're just two different representations of the same theory.
Robert, a follow-up?
I just want to make one very small comment to what you said. So these problems of lambda CDM on small scales, it's not only CDM.
That's only CDM, yes. In fact, I corrected myself at some point. Yes, it's only CDM.
No, it's not. Because you assume that that perturbations start out as adiabatic Gaussian perturbations. It's adiabatic Gaussian perturbations plus CDM. So that gives rise to problems.
Yeah.
So if you add a little bit of cosmic string,
I was assuming the standard scenario this time. One break one things at a time.
Yeah, I'm an observational cosmologist that I'm interested in the problem, the cosmological constant problem, and in ways in which it might be interesting to observe like observational signatures, and which we can help to understand and interpret what dark energy is. I came here to try to figure out the landscape from the theory side is. And I just wanted to, I had a clarifying question on what statement that you made before, that you said, it's clear that we know that there is no cosmological constant. I just wanted to ask what do you mean exactly by that statement, given that we know that lambda CDM is still comparable with most of the observations that we still, like the most prevalent theory is still the dark energy. It's not evolving with time. That's what I would call a cosmological constant.
Right, so right now, there's no observational evidence that dark energy is different from a cosmological constant. But your job is to find this evidence.
But if I don't find the compelling claims, the recent claims by no, you
have to be very careful.
I'm also skeptical.
You look at the DESI paper carefully. There's no such claim in the DESI paper.
No, but there's a hint there.
Well, that's a hint. No, it's a publicity based on the DESI paper, which
okay.
So
I wanted to comment on what you say. For example, if gravity is emergent, let me try, because it's a buzzword. I want to try to be a bit more. So you say it's basically does not allow an effective theory. Basically, to me, emergent it means that the fundamental theory is a discrete and quantum theory where the fundamental objects are not quanta of space-time, they are not gravitons. The graviton is like a collective excitation. GR is like an hydrodynamic limit of this theory. Okay. I will, in my colloquium on Wednesday, I will really give a toy model example of it. In that case, you can really see that what gravitates, what enters in the emergent space-time geometrodynamics, what we call the Einstein equation, is not the 0-point energy of the analog gravitons or the analog fields in the emergent space-time. You have to really redo the derivation, how the geometrodynamic emerge, how your heterodynamic emerge. And then you see what gravitates. And you see that there isn't a 0-point energy from harmonic oscillators of phonons on this fluid. I mean, otherwise you would have a similar problem of cosmological constant, even in hydrodynamics. You can think of it as a problem that would come up because of the phonons in hydrodynamics. Why there isn't a problem with a cosmological problem constant for phonons? Not because the fundamental equation of hydrodynamics are not the Einstein equation. Still, there is something that would determine this energy of the phonons may enter in the equation. Simply that you have to rederive what is determining geometric dynamics, and then you understand what gravitates. So from this point of view, I really feel very close to what Robert said. I mean, I think if you accept the idea that fundamentally reality is discrete and quantum, and that in a certain sense space-time could be the expectation value on a highly populated coherent state of some operator, quantum operator, then you have no reason to, you have to see what gravity is. You cannot really postulate it from the effective field theory of the emergent system. That is something that I think is pretty much clear or understood by now by people working on this. Of course, it's very difficult then to calculate from first principle what gravitates in a true quantum gravity setting. You may have, but this intuition, I think, is pretty robust by now. I totally agree with that.
What do you mean with cosmological constant problem? Because there are
normally
there's more than one problems there. So what do you mean?
Yeah, I mean, I'm just referring to the fact that when you naively take the 0-point energy and you cut off at the Planck scale or the SUSY scale, if you like, you still get a very large number, which is incompatible with observation. I'm not taking the coincident problem or stuff like that.
The old cosmological constant problem that I mentioned in my talk, for example.
Yeah, personally, I'm even a bit, I think one should debate about the coincident problem. I'm not so sure that there is, I mean, it depends the way you formulate it.
Really, so this problem is not there in modular gravity. This problem, that problem there, it's not there in modular gravity.
Yeah, because it's an integration constant, I know, but the problem is that you need still to decide this integration constant by large.
This is another problem. It's not
simply that your theory, the 0-point energy doesn't gravitate, you don't have that problem.
The cosmological problem, the problem is in your definition.
What I'm saying is that in an emergent gravity picture, imagine you get unimodular gravity as your emergent theory.
Yeah.
That will tell you, from the microscopic point of view, what is setting the integration constant.
Oh, so you're talking about another cosmological constant problem then. It's not the...
I don't know.
So, no,
I don't know.
You're talking about explaining why the cosmological constant has the value it has.
That in emergent gravity, in the way...
Two different problems, in principle.
I was not pretending to describe any problem of... I think I explained what I'm saying. If gravity is emergent with the definition I gave, then what enters in setting an eventual gravitational constant cannot be computed by the effective field theory of the emergent fields that live on the emergent geometry. It has to be computed by deriving the geometrodynamics of the emergent metric and see what are the terms that in the emergent, in the geometrodynamics that in your analogy would be exactly whatever is the theory. If you want, if the geometrodynamics is set so that the emergent symmetry is volume preserving diffeo, not just the whole diffeo, then you will get unimodular gravity. But then still your cosmological constant will be a combination of microscopic parameters of the fundamental theory, and you need to know the fundamental theory to predict how much it is. Not only, even G Newton will be emergent, and so if the cosmological constant is large or not with respect to the Planck scale,
it's possible to predict it. Even in the fundamental theory, you're not guaranteed to be able to predict it.
In the toy model of emergent gravity that we have so far, normally you can you derive from the model, you know all the fundamental microscopic.
I'm not saying that there is no model that is able to predict it.
If you have a theory of microphysics of the true quantum gravity, emergent gravity theory, when you go to the emergent layer, all your constant, even G Newton, will be a function of the fundamental parameter. So if you know the fundamental parameter, the fundamental constant, you know also the emergent one. It's not, if you're able to do that calculation, that may be very complicated.
In any emergent theory, you get a prediction for the cosmological constant. In any theory in which the metric is emergent, you always get a prediction for the cosmological constant.
In any theory, you would have some fundamental parameters, and then at an effective level, you will still have some pre-parameters. Some of them could be, for instance, the cosmological constant, right?
But think of hydrodynamics. The parameter of your hydrodynamics, if I give you the theory of the molecule, of the atoms that are underlying this, and I give you all their interaction scale, all the numbers, you can predict, for example, how much is going to be the viscosity of this fluid.
Yes, but there are some initial data you have to put in order to derive other stuff. Right.
I think that the numbers that you give in the first place for the microscopic theory are your free parameters. If you change them, the microscopic parameters
but that is an obvious objection. Of course, if you don't know the free parameter of the fundamental theory, what you can say is that knowing the emergent theory, there are many microscopic combinations that give you the same emergent. That is true.
Yeah.
What I mean is that, but if you go from top down, so from the micro layer to the emergent layer, and you know the micro layer, then you don't have problem to predict the constant in the emergent layer.
Let me be more extreme to what you said. You will find that independent of what the parameters are in the microphysics, you will always get the quantum part of the cosmological constant will always be zero.
Yeah.
Independent of the values. I think this would be.
No, I think I agree with him. I think that would be a generic feature of emergent gravity.
What does it mean? Quantum part of the cosmology?
It's something that acts on a metric like lambda G medium. That is something that you can stick onto the matter part of the Einstein equations as lambda times G mu, where lambda is a constant.
Just to follow up on this, like, is it fair to say this statement that we don't know if we find evolving dark energy, like if it's dark energy is evolving or is a cosmological constant, we don't know yet if that helps in terms of having a theory of quantum gravity. Like, does it help to have one or the other? I think, is that the first statement to say that don't help, like right now?
So I think if you find how dark energy is time dependent, that would be tremendously useful. Because it would guide the theoretical work.
Yes. It's not my field, but for example, in string theory, people are not able to get just precisely a cosmological constant. They have to have some evolving dark energy. So if this is true, this is not my field, but if this is true, then it can be useful to know when it's cosmological constant, fixed cosmological constant, or economical.
Yeah, but she's asking more. She's asking, of course, it will be informative, but how much you can pinpoint the quantum gravity theory on the base that you have dark energy rather than a cosmological constant.
Potentially, aspect I would say that is dynamical because what one measure is in the end of omega lambda, not the lambda in the effective action. So in any case, it will be a mix of lambda, if it is there, the cosmological constant, but also contributions from fields for dilaton, for instance, or any other.
And anyway, even in emergent gravity picture where it's not the 0-point energy of the excitation over the background, it's not, it's still true that it could be varying in time. I mean, it doesn't need to be truly constant.
No, let me address you. So you see, I agree with Anne that right now we do not know at all what alternative is. We only know what it is not. So any information that you can give us is absolutely crucial. So I hope you will find as good possible information about the time dependent.
But it's still, even if we find evolving dark energy, we still have the cosmological constant problem.
Yeah, well, I think that the answer is no.
And I mean, a lot of cosmologists will just say we have lambda CDM, end of story. And lambda is the value 120 orders of magnitude less than the natural scale. They stuff it in and fit. This is clearly wrong. And any hint we have that it's not the lambda that's 120 orders of magnitude less than the natural Planck scale would be fantastic. It would point that there is actually new physics there. We just have to be clever enough to work out what the new physics is. And that's all of these young people's jobs here.
I agree with you, but just to defend the cosmologist, I would say that many cosmologists do not really anymore work with the lambda CDM fitting the value. So this used to be the case, but it's not under the question and the rejection. So
okay, well, you know, if you go to say the Planck team, huge Planck team, what is it? It's lambda CDM. Of course, it's lambda CDM. I mean, you know, I have one of the leaders of the analysis up the road from me.
Yeah, but these people, what they do is a consistency check, and now they start getting criticized a lot for that. So
yeah, okay.
They try to listen.
I have a quick follow-up based on what you commented, and also connecting with what we had, I think 2 weeks ago, when Daniele Oriti was also talking in the panel. I was just curious to know what those kind of theories that you work on emergent gravity, they tell about things such as the emergence of time, for instance. That was one of the points people were also debating 2 weeks ago. If you can actually learn anything from those particular time models.
Yeah, for example, what you can show is, I mean, these two models, which are basically based on the lessons from analog gravity, if you like, which is what I'm going to work on Wednesday. I mean, you can build very easily a toy model where you give a set of fields with a very general Lagrange and which allows non-linear kinetic term. A very general, but in Euclidean, in a Euclidean plane. So the metric is delta AJ, okay? And you take perturbation around a solution, around some background solution. If you wisely choose your background solution, this perturbation fills a geometry, which is Lorentzian. So time can be basically absent at the fundamental level. You can have a Euclidean system at the fundamental level. And just the perturbation, which here are the analog of the matter, VAS, living fields of space-time, which is Lorentzian, just because you are expanding on a background which has some suitable symmetries. You can even do more. If you have this set of fields, you can select one in such a way that you get the metric are all conformally flat, flat Minkowski. And then you look at the equation of motion of these metrics, and you find Nostrum gravity, which is a theory of gravity which was proposed in 1913 by Gunnar Nostrum, which is basically as the field equation are Ricci scalar equal 24 pi g Newton, the trace of the stress energy tensor. By the way, in analog gravity, if you take a relativistic BC based on atoms which are relativistic, and so you have basically a lambda phi to the 4 theory to start with, you can show that the geometry of dynamics is Nostrum gravity. Nostrum gravity was abandoned not because it's a wrong theory of gravity, but because it doesn't predict the deflection of light, because all the metrics are conformally flat. So once it was seen the reflection of light, you know that it was too easy, it cannot be a scalar theory of gravity, the answer. I'm just saying that from that point of view, in this model of emergent gravity, you can easily see that the time could be emergent from a completely timeless, purely spatial manifold. I don't like it very much as a fundamental explanation, because I do think that even space should be emergent, not just time. So personally, I think that this is just instructive that maybe you have some fundamental reality where you have discrete and quantum objects. They condensate, they form some kind of space which is timeless, and then the time direction can be chosen a posteriori by an extra kind of symmetry breaking process by the fact that you're expanding around some solution. That could be. I'm not advocating this as just saying in principle is possible.
No, it was a question. Now a follow-up on a question on this last thing of the time, but maybe But the emergence of time, so you mentioned that you can pass from an Euclidean background, Minkowski background, to a Lorentzian signature.
No, Minkowski is already Lorentzian. I mean,
yeah, sorry.
From
I just
R4 to say from a Riemannian manifold to a pseudo-Riemannian manifold.
Okay, it doesn't matter if it's flat or not.
No, I mean, we did it for the flat for simplicity now.
But then the emergence of time is that you say it could be a signature, the fact of the emergence of time, the fact you get Lorentzian in this way, but the emergence of time is also related to diffeomorphism bias, right, which is bigger than Lorentzian. So the problem of time in general relativity, when you try to quantize it, is strictly related also to general covariance. So is that enough to just getting Lorentzian to say that you are getting some emergence of time? Or
I'm not sure I understand, because you can have a background in the. What do you mean by different variance? The mathematical statement that you have a covariant quantity, or the fact that you don't have a non-dynamical quantity apart from topology and signature?
No, I mean that in general relativity, you have a symmetry which is bigger than Lorentz symmetry. So,
yeah, but I'm not talking about Lorentz symmetry. I'm talking really a Lorentzian signature. I'm talking about minus plus 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 instead of plus 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 plus. Not even the arrow of time. Really, why time is a one-directional route instead of a bidirectional route? And it's not even the time arrow problem. It's really the basic fact why we live in, why there is one dimension which is not like the others.
Usually people, I mean, this is a very important problem, and usually people say it's a technical problem, how you can solve it. But this is a problem that exists in all fact integral approach.
Yeah.
And usually people say, it's a technical thing, we can do it, but it's very difficult. I mean, I know in the non-community geometry that was an open kind of criticism for a long time. Has been a different approach to some work, but it's a very important question in all kind of fact integral approach to quantum gravity. We are start with that.
Weak rotation, or
they say I do a weak rotation, I can do it, but do it and solve it. It is not very exactly. There is a technical thing, I do a weak rotation, but then how many papers have been done to show that you do the weak rotation fine?
What you, I mean, doing the weak rotation in gravity?
Not doing it and solving this problem.
It depends on what you mean by solving the problem.
I'm just going to,
No, I mean, I would say that if you start from the Euclidean, then it is very difficult to say that's Lorentzian. So, but you have to no, but I mean, what one can do is to do, I mean, if Euclidean is clearly easier to do the calculation than you do the calculation in the Euclidean many times. So you can attempt to do your calculation directly in Lorentzian and check if the results
yeah, but that's not exactly the same thing, right? Because your theory is in Euclidean, I want to go from the Euclidean to Lorentzian. Whether what you tell me is I work separately in both, and I saw that it's not exactly.
No, the problem is that it is not obvious, depending on your theory, that the weak rotation works. So it may not work depending on the theory, and therefore you have to test whether the results can be the same by doing the calculation independently. And if you have like a sufficient evidence that the two independent calculations give the same results, then there is a chance that the weak rotation can work.
What I just said is that it is an important question, and usually people say, I do a weak rotation and I pass Lorentzian, and that's not as simple as that.
No, it depends.
That's what I'm saying. So it's a big question in non-perturbative approaches to quantum gravity.
But on the other hand, the Lorentzian physics is defined in the theories we know as an analytical continuation from Euclidean. So if the two turn out to be not the same, it means that
but
the Lorentzian approach is not correct.
No, but gravity is, just much more.
But gravity has to include, in particular, the matter fields for phenomenological reasons. And for the matter fields,
yes,
like
but if you study like matter fields on flat spacetime, and the flat and the non-fluctuating spacetime, then okay, it can work. But as you allow for quantum gravity fluctuations, then it is not obvious anymore that we can relate that naively the Lorentzian and the Euclidean signature. Then you have to do
still, in that particular case of flat space-time, the Minkowski theory is defined as an Euclidean continuation. So if you turn out to
Okay, so this is a topic that was studied a long time ago in the domain of constructive quantum field theory. So the statement is, if you want to, that not all Euclidean theories give a well-behaved Minkowski field theory. The Euclidean field theory has to satisfy reflection positivity.
No, but
and if your theory,
I'm not saying that all Euclidean theories give sensible Minkowski theory.
the theory is defined,
something different.
the theory is defined in Minkowski.
Well, non-perturbatively, no.
Yes, non-perturbatively, yes.
No, because the path integral is not well defined mathematically.
The path integral is well defined as a distribution.
Well, as a distribution
in terms of
mathematically?
Yes.
Rigorously?
Yes, in terms of generalized functions. This is the axiomatic quantum field theory literature.
You can assume this.
There's a rigorous formulation. If the Whiteman axioms are satisfied, then the Minkowski signal for quantum field theory is well defined.
But the path integral is not.
Yes, the path integral is.
How do you define the path integral?
It's defined in terms of generalized functions.
We have three different topics still. So we have Alessia, you, and Judith. So maybe we try to be effective with time, so everyone can still ask questions.
Okay, I just wanted to refocus the discussion on quantum cosmology and involve all of the panelists. So one of your questions I really like is how can cosmology help us in testing and discriminating between the different quantum gravity theories? So I would know from the panelists about this.
Well, that was one of the points that I made, that it can actually act as a filter on the landscape of too many initial possibilities that you see, for example, from a semi-classical point of view. Quantum cosmology can actually factor out some, remove some from the competition. So that's a partial answer to your question.
Let me give another partial answer. So if your quantum theory gives a particular type of bouncing cosmology, then that will affect the cosmological fluctuations in a particular way. Whereas this emergent kind of cosmology that which I'll talk about tomorrow, so realization of string cosmology that predicts this particular consistency relation. So it's just an idea of how to go.
Yeah. Assuming that these cosmological perturbations, I mean, are explained only with quantum gravity, right? Sorry, what did you say? I mean, I think that is referring to this relationship between NT and S, right?
Well, in general, we have it. So I think you're asking if what are the quantum gravity signatures
yes.
on things that we measure today.
Yes.
And those are the cosmological perturbations. And so your quantum gravity model of the very early universe will affect the cosmological fluctuations in the gravitational waves.
Robert, but let me comment on this because I want to be sure. You see, when you say the quantum gravity models, for example, if I see the B modes, I can say that I need to quantize gravity as a quantized matter to get then the primordial spectrum of perturbation, the tensorial mode. So in a sense, I do have for sure graviton around in the sense of a quantum of gravity, but the graviton could still be not really quantum gravity. It could be the phonon of your emergent theory. You see what I mean? And so it was still, it would be teaching us about, the quantum hydrodynamics, but not about the microscopic theory of the atoms underlying the hydrodynamic limit that we live in. So I'm just, which is perfectly interesting. I just want to make a distinction that if, for example, you accept that you cannot have a effective field theory of quantum gravity, then for me, you will learn about an extra layer, which is very relevant. It's not that quantum hydrodynamics is not interesting and is useful. We see phonons, we do experiment with those. So it's a layer of reality that definitely is important, but it's not the fundamental layer yet. And I'm skeptical that the primordial spectrum of perturbation will tell you anything about that. Because in a sense, is the emergent space-time is the trace of that has the fingerprints of whatever is the underlying theory. So, for example, if what replaced the Big Bang is a big bounce, it is possible that the big bounce has some other fingerprint left. For example, there was people thinking about experiments. The vacuum may have a memory of that transition, of the fact that there is a part of boundary conditions, and maybe that there are remnants of that. But I don't think that the layer of cosmological primordial perturbation will have more about the quantum aerodynamics and not about the atomic theory. That is what I'm. And just to close up about time. There is the signature, why we live in Lorentz signature, but then that is not yet the arrow of time. And that is a problem of initial condition, because it has most probably to do with the second law of thermodynamics. But then you are back, in fact, some people call it the initial value problem. And that is definitely a problem of quantum gravity. If space-time is emergent at what we call the Big Bang, from the big bounce, whatever it is, there must be a fingerprint there. That is where we should try to see what are the deviation from the standard scenario. But it's very hard, because when you know only the emergent layer, there are many microscopic layers that can give you the same.
I think I was going to say, we have now very, very accurate cosmological prediction, cosmological observations. We've got Planck, and they're bloody brilliant. The error bars are titchy-witchy. We know the peaks and all that. We've got the gravitational waves. There's the work that is only going to get better there when they have more and more observations. And any theory that we come up with has to give us predictions that agree with the CMB spectrum. For example, if you're coming up with a new theory, Planck fitted all their stuff with lambda CDM. But if we don't believe lambda CDM, we have to come up with something better, and something that will fit all those lovely peaks.
But on lambda CDM, apart the fact that is a completely phenomenological model, and what we have done with the CMB is a consistency check. The data were analyzed in lambda CDM, so it was found lambda CDM fitting some parameters, and now the cracks in these models has appeared. This Hubble tension in my mind is nothing else than the fact that we apply the same laws in different scales in physics. So the fact that we have a problem, the lambda CDM has problems. I'm not saying it had some success, but now we see the issues. I agree with you that if we find something, we have to analyze the data in this new context, which would not be lambda CDM, and see what kind of deviation we have. But going back to what Stefano said before, I doubt it will ever be possible to find a fingerprint that would allow us to go and then match this down and see what the predictions.
This might be correct, but the cosmological perturbations have given us the CMB. Mm-hmm. And whatever you think, the CMB spectrum that Planck measured is amazing.
Well, I don't say the opposite, but
theories that replace the Big Bang, by the time you arrive at the CMB, CMB is low energy in a certain sense.
I know it's low energy, but
no, you disagree.
Is there going to be an imprint from the cosmological perturbation?
No, I disagree. We have one key parameter which has not been observed yet, namely the tilt of the tensor modes.
Yes.
But we haven't seen the tensor modes. So different universe scenarios make different predictions for the tensor. So I agree with you that if we measure a particular tensor field, then we are able to distinguish between different universe models. whether this will be the ultimate layer, microscopic layer you're talking about, or an effective layer. I agree, and we don't know, but still.
I agree with your comment. I agree with your comment. I agree with your, yeah, I see what you mean. Okay, yeah, I agree.
I wouldn't be so pessimistic about the possibility of having information about quantum gravity from future CMB observations. Because imagine that a quantum gravity theory predicts some power spectrum in a particular way, and you find this experimentally. Imagine that all the other quantum gravity theories are not able to explain this. Then you start thinking the one that explains maybe is the right theory. This is the way it works with a standard model. You have a theory, there's no reason why the theory should be like this, and then they started doing experiments, and nobody came with another theory able to explain the experiments. This is possible.
The point as well with quantum gravity is that usually what we test is a quantum gravity motivated model. We don't know the full quantum gravity. It's very difficult. Then people take either a kind of mini superspace approach or some kind of simplification. And then at the end of the day, we test the model, the cosmological model, inspired by some fundamental theory. So again, don't take me wrong, I'm not saying that we shouldn't do it. We all agree that.
This is another discussion. But whether it's easy or not to extract from a quantum gravity theory as a prediction, this is another discussion. But imagine that it's possible. Some people say that it's possible. And then a particular quantum gravity theory gives a prediction, and the other quantum gravity theories are not able to. Then you start thinking, and maybe that.
So
this is
I don't disagree
the
with
way
you,
science.
but it's the layer we are talking about. You see, the layer you are talking about, I think, is correct for what regards cosmology. If you have by quantum gravity, you mean some effective field theory, which describe matter and space-time dynamics. If you're talking about a layer which is even more fundamental, where you don't
mention effective field theories.
Yeah, but if you don't have effective field theory, I don't understand how you can, for example, again, the comment you're making. If you have, you see, imagine you have an underlying layer which is the atomic level of, then you have the hydrodynamics, which are space-time with described with the geometrodynamics and matter, which are characterized by some effective field theory. That is the layer you need to predict anything about, the CMB, the primordial spectrum of perturbation. The underlying layer, you cannot access it with the observation determined by this physics. You need other observation. I'm not saying that I don't know for sure that you can't, but your comment seems to rely on this layer.
I'm saying that you can, from these observations, you can determine the fundamental theory for sure. But the way, the way you could proceed is just. And then going and test these predictions, and maybe.
Let's agree which theories we're talking about. I'm talking about the theories of the mesoscopic layer, not the really fundamental atomic one.
Sorry, I woke up because there were two people that have been waiting for quite a while, and we're a bit stuck, and we don't have much time left. I still want to hear what maybe your question was, and also Judith's.
It was related to things that has been mentioned before. So dark matter, dark energy, and if is dark matter from a pure gravity sector or from new matter particles, admitting that we can, at a fundamental level, simplify that we can make this distinction. Okay, and my question is, as far as I know, there is an argument that shows that the critical length, let's say length, where the anomaly in the rotation of stars around the center of the galaxy start to show up. So that critical length is also related to the Hubble radius, so the critical length of dark energy, or the acceleration, if you want, the critical acceleration of the universe, if you want to express in another units. So that you can pass playing a bit with the fundamental concept from the critical length of dark matter phenomenology to the critical length of dark energy phenomenology. So I want to ask to the panelists if this is true, and also if it's true, it seems like evocative. They might be like, so it would be evocative in the sense that it seems that gravity at that scale fails. So
Say again. Sorry, I mean, I lost in the.
You're referring to the fact that a knot of Mond can be written basically it's like 1/h.
yeah, exactly. Yeah. Which is not directly of Mond, it's just this critical length where the anomaly of dark matter starts to show up, even before you start to talk about Mond. Right?
Yeah. So you're asking.
That's the argument I was referring to.
So, but what is your question basically is given this fact,
It's just a coincidence, or you have some information about it. And my intuition would say that it's required to modify the pure gravity sector without new particles.
The knot of Mond, which is where you have a new physics, is basically the reciprocal of the scale of the Hubble scale.
Let me throw the question back at you. Why are the scales the same? I don't see the scales being the same.
But there is, I can't remember the paper, but there was some paper, I think by maybe Ilgrom, which was arguing that if you take Mond and you look at A naught, which is the acceleration at which you have deviation from the Newtonian law, A naught it can be basically seen to be at the same order of 1/h.
It seems to me that they're very different.
Maybe I'm saying something wrong. Dimensionally, it should be the inverse.
Yeah.
So he was saying that they were basically they can be related, and that seems to suggest, again, this kind of coincidence that seems to relate, because it's that the Hubble scale it looks like also the Hubble scale. I have a lot of problem because some people is misled in thinking that this is an horizon and it's a. Okay. But
again, this model failed to show the transportation scales for all scales. So
but I think that you cannot think of it as A naught. Forget about Mond. You say A naught is a typical acceleration parameter where we see new physics in the rotation curves. So forget about Mond as an explanation. You say there is a scale.
Distance from the center of the galaxy, so a critical length, not only a critical acceleration. You can jump from one to another, right?
And by the way, let me just break one. I mean, I'm not a Mondian guy, but one has to say that with one parameter, they fit a lot of rotation curves in many ways way better than CDM.
Exactly.
And so, I mean, before dismissing this scale as a coincidence, I just say that
as an empirical law, it was successful.
Only at those scales, because then when you have a cluster of galaxies, you have a lot of problems.
But for this case, as empirical law was successful.
To me, it's just indicating that matter has two phases. It's behaving differently at different scale. It must be a fluid with two scales, with two different phases, something like that. It must be. Unfortunately, we like physics to be simple, but unfortunately, sometimes physics is complicated, and astrophysics is the sense of complexity, not of simplicity.
Judith?
Cosmology is simple. Astrophysics is not.
Given that the current observations are starting to be sensitive to evolving dark energy, I was curious, like if from the theoretical perspective, there are some models that are theoretically motivated, we're not fitting currently, like we're fitting the WA model that has some problems from a physical perspective. And I was just wondering, besides maybe towing models, some of the ones that people have recently started to fit, are there any others that we are missing from the observational community? The data.
Which data?
Any cosmological data that is sensitive to evolving dark energy. Like we are fitting, basically, we have models for how the dark energy should evolve in time. And we need a model that has a few number of parameters so that we can fit it. And so some of the most popular ones are WA, but my understanding is that this model was just posted at the beginning to understand the figure of merit and how sensitive each experiment is to that plane in the error bars, but it's not a theoretically well-motivated model because it moves between franchises and so I was wondering what models are there offered from the figure.
The models are without going to infinity.
I have a comment on that. So this is an excellent question. I don't have an answer, but just a warning. So these recent data have been fit using different parameterizations of the one that you're referring to, the W naught WA, and then they get certain results about the likelihood of lambda CDM. And then if you use a more physically motivated parameterization, for example, there's a recent paper about Paul Steinhardt and the student of his, there's also work in progress by a student of mine, then you get very different confidence levels of how good lambda CDM is still working.
Yes,
so
that's why I'm asking, because it depends a lot.
So you're asking exactly the right question, and I certainly can't give you the answer.
But I think that there are ways, for example, to test how lambda CDM works with cosmography. I like cosmography, for example. You assume that you have Friedmann-Robertson Walker because you assume basically a Copernican principle. And then you look at the relation between the luminosity distance and the redshift using the standard candles and rulers. So you can use supernova type 1A, you can use, standardized gamma reverse, you can use BAO, and you can use the CMB. I mean, these are different. It's very complicated to do that in a rigorous way. But then the luminosity distance scales with redshift in different way in different models. Basically, you have an expansion of your luminosity distance with respect to Z. The first term is basically related to the Apple scale. Then you have the deceleration parameter. Then you have.
So you're saying not as many models, just measure it at different redshifts.
Basically, you have an agnostic model of kinematics of the universe. Whose coefficients are determined by a given content by a given theory, not even a given content. You don't even to assume GR. If you assume GR with a given content of matter, like lambda CDM, then you will have the coefficients that you measure. You measure, you fit this curve. So you have a best fit for your coefficient of your expansion, and these coefficients are more or less in agreement with expectation. For example, lambda CDM or another model that predicts a different
Sometimes you
history.
don't have enough constraining power.
I can as well say that you can go and see a new paper by Leonora Di Valentino and Tal, and then you will see a whole list of different models.
I know.
But some constraint can be cast. It's not completely, because the farther you go out, the further you go in, and with observation we are improving, and the better you can get constrained. In some cases, you start to see some. I mean, there's people claiming that there is some tension with lambda CDM already. But what I mean is it's the matter of improving observation. At least this is model agnostic. Instead of testing yet another model, you see the history of the universe in a certain sense. Then it's a matter of the theoretician to fit that.
Okay, so we're past 4:30, and we had a lot of discussion. Also, it's quite sunny outside. Do you want to make a comment?
Yes.
Yeah.
No, I mean, I wanted to actually discuss a little bit more about this. I mean, both Robert and Stefano put out the question of effective field theories and whether we should trust or not trust them. But I would say that effective field theory by construction breaks down at the Planck scale, but still can be useful to parameterize stuff at low energies. Instead, what can go beyond the Planck scale is quantum field complete, or something beyond the quantum field theory that could be discrete approaches or string theory, anything else, and essentially anything. But your fundamental layer, using the wording of Stefano, still would translate in specific coefficients in your effective field theory. And this is how this in turn can be related to inflation and CMB.
But you see, normally you lose information going from the,
of course, you lose some details, right? But you still get something out of it, some differences. And if you are talking about fine details, it is extremely difficult to say, to test the fine details. You have to test what they give you out, like at the larger distance scales. You cannot experiment.
If the fundamental approach is predictive, then it's giving some constraint on effective theory parameters.
Exactly.
Yeah, the problem is that we don't know the fundamental. We will probably reconstruct
even fundamental approach If it is predictive, it will give constraints on effectivity
Yes.
promises that means a
Exactly.
test.
So a
Yes,
string
but-
theory will tell you that some coefficients must be 0, and asymptotic safety and quadratic gravity will give you different Wilson coefficients, and then this in turn reflects on the sub-Planckian, sub-Planck mass scales.
I guess I'm making a much stronger claim.
Uh-huh.
That simply you cannot use effective field theories on short length scales and at high currents.
That I mean, I think that you are using some assumptions. So, for instance, in string theory, depending on how fixed
This is a completely string theory independent.
then you say in cosmology
Well, I think
or in
this
general.
this is a topic for a long discussion.
It's a big topic.
Okay,
Yeah. So let me end it, and whoever wants to take to keep discussing, you're more than welcome to. Also, you can now keep discussing outside because it's quite sunny and nice. I want to thank everyone for the questions and participation, especially the panelists. So maybe we can... Thank you, everyone.